dedicated to machine learning and artificial intelligence. So it is an increasingly popular topic in our field. And today, we'll have 5 talks, which will cover different aspects of machine learning and artificial intelligence. So each talk will be about 15 minutes. So there will be 5 minutes questions afterwards. So if you have any questions, please use the chat, and then we'll go through that afterwards. We'll ask also everyone to mute and to switch off the video. And so we will start with Peter Dueben from ECMWF. So we'll give a general overview on the use of machine learning to predict weather and climate. So Peter.
Thank you very much, Frederick. So I'll try to give you, I share the screen first. Wait a second. Here you go. You should be able to see my screen now.
Yes, it appears.
So Frederick asked me to give you a general overview on the use of machine learning to predict weather and climate, and gave me 15 minutes, which is almost unfair because it's going to be, I can't cover all the topics, but I'll try to give you still an idea what potentially could be done with machine learning for weather and climate. So why would we want to work with machine learning in weather and climate predictions? Basically, predictions of weather and climate are difficult because the Earth is quite big, which means that we need big supercomputers and are still not able to represent all of the features that are actually of interest. The Earth system is complex, and it also follows a lot of nonlinear dynamics, or the different components of the Earth system follow nonlinear dynamics. And this basically means that it's kind of quite a tricky system to deal with for conventional tools. On the other hand, we have a huge amount of data available. So there's data from kind of a large number of different observation sources here. And we're talking about hundreds of petabytes of data that we store at ECMWF that are related to the Earth system, either from observations or from model simulations. So there's a lot of data there. And if you now put those 2 points together, that predictions are difficult because you have this complex nonlinear system, and also that you have a lot of data available, then you can basically directly see that if you had a tool that would be able to learn from data the nonlinear behavior of a system and could be increasing complexity as you have more and more data, this would be very useful. And machine learning, it turns out, is exactly this. So you basically can try to learn a nonlinear system, a very complex system with machine learning from data. So there are actually many application areas for machine learning in numerical weather and climate predictions. So for the different components, you can find a lot of different application areas for machine learning to look into those different details. And there are 2 different classes for machine learning that people typically talk about. The first one is supervised. What you do there is you basically learn a nonlinear mapping. So you have input and output data, and you just learn the mapping in between, which can be a nonlinear system and quite complex, actually. And that's called supervised learning. And there's the unsupervised learning, which is basically that you just provide a lot of data and you try to learn the structure of the some structure of the data and try to extract some information from this. I'm going to focus more on the supervised part, but I'm pretty sure the next talk by Marlene is actually going to focus more on the unsupervised part. And also machine learning, weather and climate modeling is actually a high performance computing application. So if you kind of look at the figure on the right here, one half of this figure is provides observations, and the other half provides a model simulation at very high resolution, which is performed at the 2nd fastest supercomputer of the world. So we're talking here really about a high performance computing application if you really want to make high resolution weather and climate predictions. And this basically means that if we would have a tool as well that could use high performance computing very efficiently, that would also be very useful. And again, machine learning actually also provides a number of advantages or opportunities, at least for us, to kind of work with high performance computing and supercomputing. So that's kind of the overall scene. Now let's go more into the specific application areas that we're talking about. So this is a plot that shows the workflow that we have at ECMWF. So you basically, we collect observations, then we have data simulation to bring the observations and the model trajectories together to generate initial conditions. Then we have the numerical weather forecast model. And then on the right, we have the post-processing, where we basically will process the output data and disseminate the information that we get from this output data to the users. And underlying of this, we have this high performance and big data processing chain, which is basically required for all of the different components within this workflow. And if you now think about where machine learning could potentially help you to improve this workflow, you actually come up with a lot of different 850 hectopascal, but also for Z500. So what you see on the right here is a CRPS, the continuous rank probability score. The lower the better. You see the results for a 5-member ensemble here in red and a 10-member ensemble. So the 10-member ensemble is better than the 5-member ensemble, as you would expect. And if you now look into 5 different solutions for the neural networks in green and blue, you will see that they're not only lower than the 5-member ensemble, but even lower than the 10-member ensemble, because we did not only correct for the spread, but also for the bias. So this is something where we kind of should look into more detail probably, because it could really help us to improve our ensemble scores. Just a note on the site, we have just yesterday launched the machine learning roadmap at ECMWF. So if you're interested in what we want to do with machine learning in the next 10 years, please let me know. There's a webpage where you will find the full text in the internet, but also the recording of the event yesterday. And if you have any questions, let me know. And in this short talk, I'm kept the conclusions very general, so I'm not going to read them out loud. And if you have questions, let me know. And thank you for your attention.
Thank you very much, Peter, for this excellent talk. Please, so if you have any questions, you can write them in the chat, or you can raise your hand if you prefer. We have time for just a few questions. Let's see if... To explain your tangent linear application?
So my audio was gone for 2 seconds, okay. I think.
That's a question from Tim Del Sol. Can you explain your tangent linear application?
Oh, yes, of course. So we have our data simulation is kind of following the 4D VAR procedure. And there you basically have the model trajectory, you have the observations, and then you basically minimize the new trajectory that you gain with data simulation by comparing to the observations in the different areas. And in this minimization process, you need a tangent linear and an adjoint code of the model. So you have the nonlinear forecast model, and to actually be able to make this minimization process, you need a tangent linear, so a linear version of the model, and an adjoint model that is kind of able to walk backwards, basically, where errors, for example, came from. And to generate this tangent linear and adjoint code is extremely difficult for nonlinear models that are very complex. So we have a couple of people really working hard to keep the tangent linear and adjoint models up to date. However, if you have a neural network, it's actually very simple to generate this tangent linear and adjoint code. So you basically just need to do it for one neuron, and then you can scale up to whatever complexity your network has. So it's much, much easier to actually generate this code. And the hope is now that if we have a machine learning emulator for a parameterization scheme, that it will be simple to generate tangent linear and adjoint code. And at least for our gravity wave track parameterization emulator, it worked very well. This doesn't mean that it will work always, but we're kind of now, the first step was very successful in this regard. Thank you.
Thank you. So there is quite a few more questions in the chat. We just take one, and then maybe you can answer the other one
Absolutely.
Directly on the chat. So next one is just, are there any other plans to investigate benefits for the seasonal timescale?
I think plans, yes. I don't think we have specific, we have started many projects. I think that's probably more for you than for me. But I mean, it's definitely interesting. I mean, we have seen you have seen that paper by Hamid Al, for example. I mean, there is something in there that you could use machine learning, and in particular for seasonal timescales, I think there is a lot of potential there. So we should look into this more.
Okay, thank you very much. So yeah, we have quite a few questions now in the chat.
I will respond to the chat. If any more questions, let me know by email as well if you're interested. Thank you.
Yes, thank you very much. So we'll go now to the second talk by Marlene Kretshmer from University of Reading. We'll talk about quantifying interconnections pathway using causal networks. Yeah, I can see your screen. Perfect.
Your full screen now?
Yes.
Perfect. Okay. So hi, everybody. So I talk about, actually not too much about unsupervised learning, but about causal networks and how one can use them to quantify teleconnection pathways. But first, let me acknowledge my co-authors. So it's Sam Adams, Alberto Ribas, Rachel Prudden, Robinson, and they all worked at the Met Office Informatics Lab, as well as Elena Sajolo and Ted Shepard, both from Reading. So, so the motivation of this work, here again, my application case is a bit more specific, so I will talk about teleconnections. And so it's, I guess, well agreed that that an improved understanding of teleconnections is really key to improve S2S predictions and also climate predictions. And so typical questions posed in this context are, for example, how much does ENSO contribute to temperature variability in a particular region, or which processes drive precipitation in another region? And so the challenge is to extract these kind of causal information from the data. Well, there are different tools available to do that. And like Peter said, machine learning and in particular deep learning are extremely powerful to extract or to estimate these nonlinear dependencies from the data, but they are not necessarily designed to answer causal questions. So that's why here in this talk, kind of advocate the use of causality and causal inference for the context of studying teleconnections. The concept of causality, or precisely causal inference, denotes the statistical discipline of quantifying causal effects from data. And well, I try to argue that this is still widely underexplored in our field. And to kind of motivate this causal approach in more detail, I'd like to go back to this term teleconnection, and here I show the parts of the definition from the AMS glossary. So here, teleconnection is defined as a significant correlation in widely separated points, with the name referring to the fact that such correlations suggest that information is propagating. Well, we all know that correlation does not imply causation, but I do think that this definition kind of reflects this gap that there is currently. So on the one hand, there is like a large gap between our statistical descriptions of teleconnections, which are mostly correlational, and our physical understanding of them, which are causal. So the question is kind of how can we reconcile these two concepts? And again, I think there this causal inference framework is extremely helpful. So let me briefly explain how causality is defined in statistics. It's actually very intuitive. The process X is said to cause Y if intervening in X changes Y while keeping everything else fixed. And this intervention can be described by this do operator where you see there. So, and obviously, I will show this, that the interventional probability distribution after doing X is not the same as the probability density function of Y in general. For example, consider this very simple example. So where X denotes pressure at some location, and then we have a barometer Y. Then obviously, if I intervene in Y, so for example, I could just by hand put the needle of the barometer and just move the needle around, then this will not cause any changes in X. So I can intervene in Y, I can do Y, and this will not change the outcome of X. On the other hand, if, I don't know, while doing some geoengineering, if we change the pressure at the location, or if we change something with the sun, if this was possible, this will indeed, of course, cause changes in Y. So in this case, X does cause Y, and we can again express this with this operation. So what causal inference is that it the discipline to kind of predict the effect of an intervention from observed data, without actually doing the intervention, because like in this case, interventions are more like thought experiences, so they're not always feasible. And of course, this kind of concept of doing intervention is the same as doing targeted model experiences. But obviously, often we are just interested in these model biases. So that's why I think causal inference is also useful here. And the key point I try to make also in the next slide is that kind of answering these causal questions, so kind of predict effects of intervention, is only possible if we have some kind of causal knowledge about the data generating mechanisms. For example, if we had data available of X and Y in this case, there's no way we can predict intervention. Only if we know that, like in this case, that X is causing Y, we can make such predictions. So before I give some more concrete examples, let me just give an overview of the different steps of causal inference. Given that also this name knowledge-guided machine learning framing is used a lot, I also like to think of this as knowledge-guided statistics. So the first step would always be to use your expert knowledge to set a plausible causal model. So the different nodes represent different processes, such as ENSO or temperature in a specific location, and the arrows denote kind of the assumptions or hypotheses where there are some causal interactions. And then the second step is that we can now make use of these explicit hypotheses or assumptions and draw some logical implications to see if the data we collected, for example, our observation data or model data, support this network. So in this case, for example, you can see that the processes U and V, they are not directly connected, but they do have a common driver X. So, but once we control for X, so once we kind of block this influence of X, and in the linear case, we could just, for example, calculate the correlation, so the partial correlation and conditioning on X, we would expect them to be, so we expect this correlation to be 0 then. And so we can kind of use this as a sanity check to see if our model makes sense. We cannot test all the assumptions, but we can test the ones at least which are testable. And then, of course, also have to maybe update the network if necessary. And then the important point is, or the important step is then that we can use these causal inference rules to estimate causal effects. And again, keeping this example of the network on the left, if we're interested to estimate the causal effect from X to Y, based on that, but we can see that there's just one pathway, which is via U. But we can also see there is a common driver Z. So we have a common driver of both X and Y. So we have to account for this effect. And again, we can do this in the linear case very easily by just including it in our multi-linear regression model. And then we can indeed interpret this regression coefficient A as the causal effect from X on Y, of course, based on the assumption of the causal model. Because the idea is really that this interventional distribution or this interventional probability distribution is hidden in the data we have, but we do have to kind of extract or control for the factors which dilute the causal effect we are aiming for. Okay, so this was so far very theoretical. So I tried to make this more explicit with some very basic or almost trivial examples from actual teleconnections. So the first, and I should say this is using ANSYM analysis data. So the numbers are based on real data. So in the first example of a common driver, we have data of summer precipitation in Denmark and the Mediterranean, which are significantly correlated, correlation coefficient of -0.25. But again, we would not interpret this as a causal relationship because we know that precipitation in both regions are affected by the position of the North Atlantic storm tracks, as for example expressed by the NAO. So indeed, we can check this, like say this, this assumption, and calculate the partial correlations, and we would indeed find that once we control for the NAO, the correlation between precipitation in these regions actually drops to 0. So let's say this model our intuitive model is also supported by the data. And then again, we can also, let's say, based on this model, estimate the causal effects and actually interpret them also as causal effects. So for example, assuming this model is correct, or if we agree on the model, then we can agree on the assumption of linearity. We can actually quantify the causal effect of the NAO just by regressing it onto Denmark precipitation and also on Mediterranean precipitation. And these are standardized causal effects or standardized regression coefficients. And one important point is also, which I think is often overlooked, is that we can actually interpret these simple causal effects. We can also use them to explain the association we found in the beginning. So the product of the two effects is the same as the correlation between them. So the association or correlation is just inherited from the different causal effects. But again, I think, this is a very, very simple example, but it shows how we can use our knowledge to kind of interpret the data we have and then to actually draw causal conclusions. To give a second example, that is a mediator where you see the conditioning on and another driver max actually can also be harmful. Consider this example where we are interested in the effect of ENSO on California precipitation, and the network on the right shows the underlying or assumed causal model. Well, it's probably not too controversial, so that ENSO affects the position of the jet stream in the North Pacific, which in turn affects California precipitation. But what we often do when, for example, not considering such a causal network, is that we just throw in all our different climate indices and to make the best prediction, or which is in the predictive sense also not a problem. But if we, for example, use ENSO and the jet or some jet index to in a regression to describe California precipitation, we cannot, or we find that the regression coefficient is 0, which obviously makes no sense. In this case, we can definitely not interpret this regression coefficient causally, because what happened here was that by including the jet, we kind of blocked the pathway from ENSO to jet stream. So we actually regressed out the pathway we actually wanted to measure. So the correct way in this case would be to actually not include the jet and just directly regress ENSO on California precipitation, and then we get this this better estimate of 0.24 of the causal strength of this relationship. Alternatively, we could also, again, using this path tracing rules of this linear property of linear models, we could also estimate the link strength of the individual links. And for example, first calculate the link from ENSO to the jet, and then from the jet to California precipitation. And then again, this the product of the two, so the product along the pathway is the same as estimating the total effect. Okay, so I give a third example. This is of indirect and direct effects. So this is again showing ENSO, and the effect on the jet stream, but this time in the southern hemisphere. So we see this effect, this direct effect from ENSO to the jet, and there's also this called stratospheric pathway. So ENSO is known to affect the breakdown, the time of the breakdown of the polar vortex, the SBV, which in turn also affects the jet position. We could again estimate the total effect of ENSO on the jet stream, actually quite easily. There are no confounding factors, there are no common drivers, for instance. So, and we find the total effect to be 0.14. But often one is also interested in the different contributions of different factors. For example, we could be interested only in this direct tropospheric pathway. In this case, we do have to control for this mediating pathway via SBV. And we can do this by including the SBV simply in our regression model. And then find that the effect of ENSO is only 0.04. The effect of ENSO via the troposphere is only 0.04. Similarly, we can also estimate, or we can quantify this indirect pathway and estimate the effect of ENSO on the SBV and also of SBV on jet. For the latter, we do have to account for the common driver ENSO, as we can easily see from the network, kind of block this effect. And then the stratospheric pathway is again just the product along the pathway, and again this property of linear models. The sum of the two, so the tropospheric plus the stratospheric pathway, is again just the same as the total effect of ENSO on the jet, which we found at the beginning. So kind of the point here is that since we acknowledged this model or this our hypothesis in the beginning, we can really, let's say, in a very systematic way, quantify these different contributions and interpret the data, in this kind of transparent way. Well, an obvious criticism could be that these are very simple cases. This can be more tricky. I want to highlight a paper which was recently accepted, where we kind of try to quantify the effect of Benson-Kara CS concentration on future polar vortex changes in CMIP5 models. And here you just, from this network, which we state, you can see that things are a bit more tricky, and that we also have, coupled, since it's a coupled system, there are different feedbacks. And in this paper, we also kind of, or autocorrelation also plays a role. We kind of, we discuss how one can deal with these kind of issues by using time lag data. And then I just very briefly want to give one slide to links to machine learning, because again, so far this was basically, very simple regressions. Well, another criticism is that it's nice that we can make these causal statements from our causal assumptions, but often we don't have such a causal model. And this is where causal discovery algorithms come into play. So assume our input data is that we only have these time series data of these different processes. And what we want is to learn the causal structure from the data. And again, there's something called causal discovery algorithms, which have which is also, let's say, comes from the same discipline of causal inference and causality, and uses, or is based on the same concepts, but there with some additional assumptions, it's actually possible to go from the left to the right and kind of learn the causal structure. I've been mostly using the so-called PCMCI algorithm, where the idea is that one iteratively tests or iteratively goes through different combinations of conditions to learn the causal structure. And this is also expanded more and more. It can, for example, deal with autocorrelation, but also with different regime dependencies, instantaneous links, etc. And I suggest you follow the work by Jakob Runge for the code and tutorials. And then, kind of an outlook, I think one way also to further combine this with machine learning is to not only have to learn also these time series indices or these relevant regions from the gridded climate data. We have some papers and also some applications, I mentioned some below, where we kind of try to do this, that we first extract patterns from gridded climate data, extract these relevant regions, and then to learn causal structures or causal predictors. But I think there is a lot more potential to use the power of machine learning and deep learning in particular to learn these patterns from the data. So kind of to conclude, I talked about causal inference, which is on this intersection with machine learning statistics. And I thing is one has to explicitly embed hypothesis in the data analysis. But I think this then, even while using very simple linear tools such as regression, one can actually, I think there are like a variety of different opportunities how this can be useful. First of all, it gives a very easy and traceable approach to quantify teleconnection pathways. And this, of course, is then also useful for model evaluation, understanding signal-to-noise issues, bias adjustments, and so on. Actually, I've been working more in the past on causal discovery algorithms, and I still think that these are also very useful to help closing knowledge gaps, especially when it comes to learning relevant timescales of interactions. And lately, I'm also quite enthusiastic or looking forward to combining these tools with deep learning and explainable AI, but this is for another talk. So thank you for your attention.
Okay, thank you very much for this excellent talk. So please, if you have any questions, please you can write your question in the chat or to raise your hand if you prefer. Well, what I propose is that we continue. I mean, if people have questions, there is a question here. I would like to better understand why causal discovery algorithms help to find new links on gridded data, but not on time series.
Sorry. So I'm not sure I understand the question, because the idea of causal discovery algorithm is exactly that, to understand on the time series the causal structures, or to learn based on your time series, learn the causal structure of them. I do think it's not always straightforward which processes to include, and this is probably also the most crucial part of learning something meaningful. And of course, we can use the indices we know, or we can interpret, but there might be also other potential sources of predictability which might be relevant. And I see, in the context of teleconnection, in the context of causal discovery, I think there's a lot of potential for machine learning, kind of pattern recognition, or pattern extracting patterns to learn new sources of predictability and kind of combine them with the knowledge we already have, for then providing this kind of causal evaluation. But I'm not sure if I understood the question correctly, or I hope this answers the question.
Okay, we can go to the next one from Ben Cash. Maybe Ben can talk directly.
Let's see if I can. My audio has been a little bit iffy.
Yeah, we can hear you.
Okay, great. I was wondering about the case, thinking about some of the ENSO causal networks you showed, if there is another potential confounding factor you're not aware of when you're constructing that. How does that affect your results?
So I think it's very much possible. So in a different ways forward, let's say. I think, or on the one hand, in the methodology, it's also possible to include latent variables and make assumption on this, or just based on this, see how much this would be affected. Or so let's say the methodology is way richer than things are presented. I think very practical thing would be to just see if one does, let's say, these predictions or these regression models, to just see and test if the residuals are still show some structure, which then would force one to think about other confounding factors which might play a role. So this would be, let's say, my very practical attempt to deal with that. And then, but yeah, again, highlighting that I think the key point is not to say that the model has to be completely correct, or that only if one knows a model, like a causal network, one can do such inferences. But I think the point is more that one can test different hypotheses using this kind of framework. And then one can challenge the assumptions one made at the beginning. For example, if one has good reason to challenge the assumption, the causal networks I presented, because there are other confounding factors, I think that this is just like a more systematic way to then test these different possibilities without, let's say, in contrast to this implicitly.
Okay, thank you. I think you have quite a few other questions, which I think you can answer directly on the chat for the sake of keeping on time. I think we'll go to the next presentation from Zheng Wu from ETH Zurich.
Hi everyone, I start to share my screen now. And now can you see my screen?
Yeah.
Okay, perfect. Thank you. So hi everyone, it's my pleasure to present our work here in today's webinar. So our work is about using a mode decomposition diagnosis to find the signals of stratospheric extreme events. And these signals from here can potentially be used to improve the predictability of these extreme events in subseasonal to seasonal timescales. And one of the main extreme events in the stratosphere is sudden stratospheric warming. We call it SSWs. This is what we focus on in this study. And SSW is extreme circulation in winter stratosphere. And here we use one SSW as an example. The plot and the animation shows the potential vorticity at 10 hectopascal. And the high values of PV is shown in pink, and it represents the polar vortex, which is the westerly center at the polar region in wintertime. And in some winters, the high values of PV separate into two parts. And when this happens, it represents the polar vortex split into two daughter vortices. And this is called the disruption of the polar vortex. When this happens, there's an SSW event. And the disruption of the polar vortex means the normal westerly flow reverses to easterlies. In this winter, we also have an SSW event. And now we will show the polar vortex strength, the time evolution of the strength of the polar vortex, which is usually represented by the zonal mean, zonal mean at 10 hPa and 16 knot on the left panel. The black line is the climatologies of the polar vortex strength, and the red one shows the strength of this winter. As you can see, in late December, there's a strong deceleration of the zonal wind, and in early January, the wind reversed to become negative. And when this happened, it indicates an occurrence of the SSW event. Accompanying with the deceleration, the reversal of the zonal flow, the stratospheric temperature also increased by tens of kelvins in just a few days. Here we show the time evolution of the polar cap zonal mean temperature at 10 hPa on the right panel. Again, the red color is the temperature of this winter. In late December and early January, there's an abrupt increase of the temperature, leading to a much warmer stratosphere than the climatologies, which is this black line. And SSWs are caused by the interaction between the upward propagating of planetary waves and the mean flow. And according to the dominant wave number component of the planetary waves that lead to the breakdown of the polar vortex, SSWs can be classified into wave number 1 and wave number 2 event. And here we show the spatial pattern of PV at 850 Kelvin. On the left, it shows the PV composite of wave number 1 event. It differs by the vortex displacing off from the pole to mid-latitude. And on the right, it shows the PV composite of wave number 2 event. And it is featured by the vortex splitting into 2 parts. And this is what we saw in the animation. Now the question is, why do we care about extreme events in the stratosphere? Because previous studies show that the stratospheric anomalies can propagate downward to the troposphere and influence the weather in the troposphere and at the surface. For example, this figure is from a study by Butler in 2017. It shows the stratospheric anomalies downward coupling to the surface. The x-axis shows the days before and after the SSWs, and the y-axis shows the pressure. And the dashed line shows the first day of the event. As you can see, the anomalies can reach the surface, and the impact lasts from weeks up to 2 months after the onset of the event. Because of this, SSWs are thought to be an important source of predictability for the tropospheric weather. However, SSW itself is difficult to forecast. This is a figure from a study by Dueben in 2020. It shows the predictability of SSWs with various lead times, as shown in the x-axis. And the y-axis shows the percent ensemble members of 8 different subseasonal to seasonal models that can correctly predict SSW events, and which color represent one S2S model. And the black line shows the multimodal mean of the percent ensemble that can capture the event. You can see with lead times of 1 week to 2 weeks, more than 50% of the members can capture the event. While with lead times longer than 2 weeks, less than 40% of the members can predict the SSWs. This figure suggested that the predictability limit of SSWs is around 1 to 2 weeks. Now we separately to look at the predictability of wave number 1 and wave number on the left panel and wave number 2 event on the right panels. Comparing these 2 panels, you can see the predictability of these 2 type of event is different, with higher predictability in wave number 1 event, and the SSW and wave number 1 SSW are predicted at longer lead times. Oh, sorry. Can you still see my screen?
Yes, yes.
Okay. As wave 1 SSWs are predicted at longer lead times than wave 2 SSWs. So the goal of this study is to find the signals of SSWs that are distinct from the normal winter days with lead times longer than the current 2 weeks predictability limit. And we also want to find the signals that are distinct between wave number 1 and wave number 2 events, such that we can use this signal to predict the type of events with longer lead time. So in order to achieve our goal, we use a method called multi-composition diagnosis to find the signals. First of all, we introduce the anomalies tells PV equation as shown here. P is represent PV, and V is the wind vector field, and overbar is the daily climatologies, and prime is the daily anomalies. Here, the first term shows the PV anomalies tendency, and the second and third term shows the linear PV aversion term, which involve the interaction between one climatologies and one daily anomalies. And the fourth term is the nonlinear PV flux term, which involve the interaction between two daily anomalies. And F prime is calculated as the residual. Now, next, we use the mode decomposition method proposed by Akiva in 2019. We apply PCA on the PV anomalies to obtain the EOF mode spatial pattern at the EOF spatial patterns of PV at 850 Kelvin, and denote these EOF modes as E's. And then we calculate the corresponding principal component time series and denote this PC as A's. Then we regress the wind vector field onto these PCs and take the inner product. And take the inner product with the first EOF mode to obtain the PC tendency equation for the first principal component A1. And what we get is called the mode equation budget. It's shown in the equation below. On the left, it shows the A1 tendency term, and C1 is the eigenvalue of the first EOF mode, and these two terms correspond to the linear aversion term, and this term correspond to the nonlinear aversion term, and F is the residual. And then next, we further combine these two linear aversion terms as the total linear aggression, as the total linear aversion term. And then we further separate it into with the contribution only from low frequency EOF mode and the interaction only from the high frequency EOF modes. And similarly, we also decompose the nonlinear PV terms into the interaction only involve low frequency EOF modes, and interaction involve low and high frequency EOF modes, and interaction only with high frequency EOF mode. And then in the following study, we will see how each of these terms contribute to the change of A1. And in this study, we will only focus on the 10 equations for A1. And now let's take a look at how the first EOF mode looks like. It is shown on the upper panel. The first EOF mode takes the shape of a zonal symmetric structure with a negative anomaly centered at the pole. And then we look at the corresponding first principal component A1 of the ERA interim winter daily data, which is shown in the bottom panel. The x-axis shows the winter days, and the y-axis is A1. And the positive values of A1 indicates the weakening of the polar vortex. And this red line indicates the first days of SSW events. And as you can see, when approaching to the SSW days, A1 gets larger and larger, leading to a very positive value of A1 on the first day of SSWs, indicates the disruption of the polar vortex. The reason why we focus on the equation budget for A1 is because it has the strongest relationship with SSW events. Now let's take a look at the results. We performed the budget analysis for A1 of PV onto the concatenating ERA interim daily data from 50 days to 1 day before all the 25 SSW events in 1979 to 2018. And we showed the equation here again. On the left panel, we show the time evolution before the onset of SSWs for each term in this equation. And the A1 tendency term, which is this black line, start to increase before 25 days before the event. And it becomes larger and larger when approaching to the central day, leading to the breakdown of the polar vortex. And the increase of the A1 tendency is mainly contributed by the linear term, which only involve the low frequency EOF modes. And the second important contributor, which is this red line. And the second important contributor is from the nonlinear term that only involved interaction between low frequency EOF mode, and it's this green line. And next, we combine all these linear terms together and all the nonlinear terms together, and the result is shown on the right panel. So as you can see, the linear terms start to increase at the same time, as the A1 tendency term. It starts to increase from 25 days before the event. And the nonlinear terms start to increase from 10 days before the event, and it becomes more and more important after that. Now let's specifically look at the A1 tendency budget for the composite of wave number 1 event on the left and of wave number 2 event on the right. And as we can see, the increase of the A1 tendency term in wave number 1 event is mainly contributed by the linear terms, while for the wave number 2 event, the linear term is important in earlier stage, but from 10 days before the event, it decreased dramatically, and the nonlinear terms increase rapidly and becomes the dominant contributor to the increase of the A1 tendency term. And from here, we can roughly separate the vortex weakening process into 2 different periods. The first period is from 25 days to 15 days before the event. And in this period, the linear terms is important in both wave number 1 and wave number 2 events. And the second period is from 10 days before the event to the onset day of the event. And in this period, the relative importance of linear and nonlinear terms in wave number 1 and wave number 2 events is very different. And now we try to examine the significance and robustness of this different importance of linear term and nonlinear terms in these 2 types of SSWs. So we bootstrapping all the wave number 1 event and all the wave number 2 event respectively. And here we show the result of the bootstrapping. On the left, it shows the linear terms, and on the right, it shows the nonlinear terms, and as a function of lead times. And the thick line and the shading shows the mean and plus and minus 1 standard deviation of the bootstrapping respectively. The black line is the composite, the red line is the composite of wave number 1 events, and the black line is the composite of wave number 2 events. And comparing these 2 panels, you can see there's no overlapping in the shading of wave number 1 event and wave number 2 event in both linear terms and nonlinear terms from 10 days before the event. So this demonstrates that the distinct behaviors of the linear and nonlinear terms in the wave number 1 and wave number 2 SSWs. And before we summarize our study, we try to interpret the signals from this mode equation budget dynamically by connecting with the PV flux. The reason why we try to connect with the PV flux is because the zonal mean PV flux is directly related to the divergence of Eliason prime flux, and thus can be directly related to the change of the zonal wing. And therefore, here we show the density weighting zonal mean PV flux and decompose it into the equation shown here. The C represents daily climatologies and A represents daily anomalies. And the blanket is the zonal mean and the star is the deviation from the zonal mean. So we decompose the zonal mean PV flux into its climatological component, its linear component, and its nonlinear components. And then we show the time evolution before the SSW event for each of these terms for the composite of all SSW and for wave number 1 SSW and for wave number 2 SSWs. As you can see, when approaching to the central day, the total zonal mean PV flux, which is this black line, become more and more negative. And this more and more negative PV flux is mainly contributed by its linear component in wave number 1 event, and it's mainly contributed by its nonlinear component in wave number 2 events. And this result is consistent with what we gain from the A1 tendency budget. Now, come to the conclusion of this study. By using the mode decomposition diagnosis, we we are able to find the signals of the PC1 tendency, starting to increase at around 25 days before the events, which is beyond the current 2-week predictability limit of SSWs. And at the same time, in both win number 1 and win number 2 SSWs, the increase of the PC1 tendency is mainly contributed by the linear aversion term, which provides equal predictability in both types of events. And from 10 days before the event, the distinct behavior of the linear and nonlinear aversion terms in win number 1 and win number 2 events can help us predict the event type with lead times of 10 days to 1 week. And in our next step, we try to apply these methods to the S2S models and then to examine whether we can actually use these methods to improve the predictability of SSW event and their correspond and their different type of events. And this is some reference of the study, and thank you for your attention.
Okay, thank you very much. So again, if there's any questions, please write them into the chat or raise your hands. So usually there's always a bit of a delay between the questions and the talks. So what I propose is maybe we switch to the next speaker and then you can answer then your questions into the chat. So next speaker is Michael Sheuerer.
Okay, can you hear me and
Yes.
see my screen already?
No, not yet. Yes, starts to be there, yeah.
Okay, that's good.
It's not full screen yet. Yeah.
Okay, how about now?
That's now, yeah, we can see it.
Okay, great. Yeah, thank you for giving me the opportunity to give that talk. I should say first that my affiliation has changed recently, so the new affiliation is already shown here, but this research has still been performed and paid for by NOAA and the California Department of Water Resources. And in this project, we have explored artificial neural networks in the context of post-processing subseasonal precipitation forecasts over California. Traditionally, the type of methods that we have used for statistical post-processing are parametric and are basically a more complex version of regression where you relate different predictors derived from the ensemble, like the ensemble mean and the ensemble variance, to a family of distribution that then describes the probabilistic forecast. And this has worked quite well, but it's usually performed grid point by grid point. And we felt that in a subseasonal context, it would be good to make more efficient use of the overall data and kind of share data across different locations. And that turned out to be relatively difficult with these models and the parameters that don't always have a straightforward interpretation and therefore not a straightforward connection across space. And that's why we tried a different approach based on neural networks. To do so, we first did some pre-processing of the data. And in this particular case for precipitation, we thought it would be a good idea to first discretize the observations. So what you see here in this example is a transect, latitude transect in California. And the percentiles of the weekly accumulated precipitation. And in order to discretize this in a way that the different categories are populated more or less equally across different locations, like both wet and dry climatologies, we introduced a 0 precipitation category, and the rest was divided equally according to the percentiles that divide the remaining probability. And that way, we now get 20 precipitation categories, and those are the categories that we are trying to predict by the neural network model. As a predictor here, we use precipitation forecasts from a numerical weather prediction model. Here, actually, the ECMWF model, because the NOAA model wasn't available at the subseasonal timescale at the time of this research. And in order to condense and normalize the information in the ensemble, we calculate the extreme forecast index of ECMWF ensemble precipitation forecasts. And we thought that that's a nice way, because the extreme forecast index does exactly that. It puts things in a climatological context. So independent of the location where it's forecasted, tells us whether precipitation is like low compared to the model climatology in this case, or large compared to model climatology. And in addition, we use longitude and latitude as predictors in order to allow the model that is now shared across locations to still have characteristics that can vary across space. And one of the advantages of neural networks is that they can model these nonlinear interaction between different predictors and use this longitude and latitude information to construct a model that still has a locally dependent response. We also use climatological probabilities, and the rationale for that is that we already expect relatively low predictability at the subseasonal timescale, and in that case, the best we can do is always to revert back to climatology. And arguably, a goal of post-processing should be that at least we're not doing worse than climatology. And so we offer climatological probabilities to this neural network at the very end, and essentially we model probability anomalies from those climatological probabilities. So the baseline is climatology, and then if we find a useful signal in the forecast, we try to increase or decrease those probabilities. An example of this is shown here for a particular location during an atmospheric river event, when we compare the forecast probabilities that we get with lead times 2, 3, and 4 weeks. And we see here that with a 2-week forecast lead time, we still get a relatively strong signal, and a relatively strong shift here towards high probabilities of precipitation. But then for longer lead times, we lose the confidence in our forecasts, and the probabilities revert back to the climatological probability. The next step is now to turn these class probabilities, which have been convenient and useful for statistical purposes, but are kind of hard to interpret because they depend in weird ways on the location and on the local climatology, to turn this back into full predictive distribution from which we can derive any quantity we like. And we found that very basic linear interpolation can be used. First of all, we can calculate the cumulative probabilities by just summing up the category probabilities that's shown here in the plot on the left-hand side. And then if we transform this with a particular transformation, it turns out that for this particular weather quantity, those lines straighten out and then can be interpolated relatively well with just a linear interpolation. And then if we reverse that transformation, we see that we get a decent interpolation of the predictive CDFs. And once we got those, we can derive any probabilistic forecast quantity we like. So for example, we can calculate probabilities of exceeding a certain percentile. And now this percentile is uniform across space, so it doesn't have this dependence on the local zero precipitation probability, so it's more interpretable. But we can also choose a fixed threshold. Here we chose a relatively high threshold of 6 inches of precipitation in 1 week. And then we get the climatological imprint in these probabilities, where the probability of exceeding this amount is higher in areas that generally have a wetter climatology. Here's an example for a 2-week precipitation forecast. If we go out to 3 weeks, we see similar figures, except that the probabilities are much closer to like the climatological probability, which just shows again that we lose confidence in the forecast and we issue something that is closer to climatology. Now, this first approach was still like a classic post-processing approach in the sense that even though we share information across or share a model across different grid points, we still turn an ensemble forecast at a particular grid point into a probabilistic prediction at this grid point. But in the subseasonal time scale, one can argue that maybe the displacement errors become so big that instead of even looking at the precipitation forecasts, we should rather look at certain large-scale predictors, as there may be a better chance that the forecast systems get those right, and then relate these large-scale predictors to the precipitation on the ground. And this is what is illustrated here, where as examples for large-scale predictors that we think is related to precipitation, we took total precipitable water, total column water, and geopotential height anomalies, which we feel inform the atmospheric flow and the available moisture, and we try to relate that to precipitation. For this, again, we use neural networks, but now a special type of neural network is particularly suitable for that task, the so-called convolutional neural networks, which have been designed specifically to interpret image information. And our large-scale predictors are essentially that. They are basically a 2-channel image of these 2 variables. And so we're trying to train this neural network to translate this image into precipitation anomalies. One thing that changes now that we're not transforming this information grid point to grid point, but our predictor is a whole image that needs to inform like all of the grid points simultaneously, is that we now have to define a number of basis functions so that the image can inform precipitation in different parts of our domain of interest, here California, in different ways. So the basis functions here just project on different parts of California so they can react differently to a certain large-scale atmospheric pattern. Another thing that we're doing is that we think that at these lead times, looking at the ensemble mean may not be as reasonable, because the different ensemble members typically diverge so much that that the signal, and especially the features in an image that could be interesting, get smeared out too much if we just average the different members. And also those features might be difficult to learn at the subseasonal timescale where we expect the errors to be relatively large. So instead, what we're doing is we train this convolutional neural network against analysis, meaning like analyzed geopotential height anomalies and total column water. And in a second step, we then run the ensemble forecasts separately through this convolutional neural network, so that every single one of these members now produces a probability. We kind of average those probabilities together. And because this is somewhat of a perfect proc approach that doesn't take into account that the ensemble itself may already not perfectly represent uncertainty, we do an additional adjustment to obtain reliable forecasts. Now, this is illustrated here briefly. So we have the different members here, 11 members, for which we have hindcasts. And then each of these members is run through the convolutional neural network and gives us a precipitation anomaly over California. We average those together, adjust in order to account for uncertainty that is not fully represented in the ensemble, and we get finally an anomaly that we add to our climatological probabilities. Here we take a look at reliability diagrams for both of these methods. So the conventional neural network approach that it translates precipitation forecasts directly into precipitation, and then this convolutional neural network that uses these large-scale predictors. And we also compare with this parametric approach that we have used and are still using at the medium range. And we see here that for below normal and above normal 1 week precipitation accumulations at the different lead times, they're all more or less reliable. Like for the longer lead times, it looks like the curves are a little bit off the diagonal, but you can see in the frequency of usage diagrams that also the reliability diagrams themselves may be subject to a lot of variation, because we're barely departing from climatology at these lead times due to a relatively weak signal. Here's a look at ranked probability skill scores over a number of climatological percentiles. Here, the below normal, above normal, and also the 85th percentile, because that is something that our partners at the Climate Prediction Center like to look at. And we see that unlike the parametric method that struggles for extended lead times to even be like as good as climatology, presumably due to overfitting, we see that the two convolutional neural networks that have this inbuilt regression towards climatology always manage to have at least 0, but often a slightly positive skill. However, we also see that the skill for extended lead times is relatively low, and so that motivates to look further into additional sources of predictability that we haven't explored so much here in this work. Here's the same in a table form, where we have averaged across space, and this shows a little clearer that during week 3, actually both week 2 and week 3, this more conventional neural network approach is better, and then week 4, the approach that uses the large-scale information as opposed to precipitation forecasts from the forecast systems directly actually gets the best results, but again at the relatively low level. Here's just a summary of what we looked at. So we've constructed these neural network approaches with the goal of sharing a model across different points in space so that we can make more efficient use of the data, while also addressing local characteristics. And this alternative neural network can not just use grid point by grid point transformation of forecasts, but also use large-scale information that comes in the form of images. As I said before, the skill is still limited. Week 3 and 4, we managed to always beat climatology, which is the minimal bar, but sometimes we're not far above that bar. And so the next step would be to explore whether additional predictive information could be useful and could be integrated to increase the subseasonal forecast skill at the longer lead times. That's it for my talk. Thanks for listening.
Okay, thank you very much. So I can see there is already questions for you from Arlan Dixon. Arlan Dixon, do you want to ask your question directly? Okay, so in audio. Okay, so the question is, how are you choosing your training data temporarily for the CNN approach versus an AMOS approach? So how are you choosing?
I think the training data is chosen in a relatively similar way, except that specifically for the CNN approach, again, we have this 2-step procedure where we train against reanalysis. But other than that, we typically try to have a certain seasonal window. So even though we try to remove certain climatological characteristics, here we have only looked at the cold season, and it would probably make sense to have a different model for different seasons. And then we just, in the standard neural network case, we still have hindcasts, which we need to increase our data set. And for the convolutional neural network, we just make sure that we have several years of reanalysis data that we can pull together to train like a neural network. But the general principles of composing the training data are actually very similar. The main difference here is really that the model is applied simultaneously to different grid points, whereas for the EMOS approach, every grid point gets its own set of.
Okay, and there is a second question for me. Are both limited by sample size in the same way?
So the hope here was that, so I should say generally a neural network approach or like these modern machine learning approaches, because they have more degrees of freedom, they would actually typically need more samples. So it's kind of counterintuitive to use that in a situation where we have a relatively poor signal to noise ratio, which means like a lower effective number of samples. And the reason why it still works here is this ability of pooling samples across space. So when we do this grid point by grid point, we only have the sample size that we get by collecting training data across time, like across the hindcasts in a certain temporal window. And here we use training data pooled across all grid points in space. And that means like we get a relatively large sample size for this standard neural network. Of course, we have no spatial pooling for the convolutional neural network. And that's why we chose to fit those two reanalysis, so we get a better signal to noise ratio, and we kind of exclude the forecast error during the first step.
Okay, thank you. You have quite a few questions ongoing, so I will leave it to you to reply to them in the chat. I think we'll move to the last talk of today's, which will be given by Andrew Robertson, which will be on the S2S AIML competition in 2021.
Can you see my screen?
Not yet.
Can you see it?
No.
Let me try again.
Yes, starts to come.
अच्छा
Okay,
Yes.
great.
कोई मसला नहीं, वो है मेरे पास, लेकिन वो मेरे उस पे पड़ा हुआ है, तो मैं वहां से उसको इधर
I hear some voice. Somebody can mute the microphone, please.
हाँ, मंथली मीन्स आना है, क्योंकि डेली तो बहुत ज्यादा हो जाएगा.
Okay, so we thought we'd end the
ग्रेट
webinar.
वो कोई इशू नहीं है, वो आप मुझे बता दें तो मैं उसको बल्कि सेट
Please,
कर
could everyone mute their
दूं.
microphones,
सीजन अगर
please?
स्पेसिफिक हो ना तो डाटा साइज छोटा हो जाता है.
Can everyone mute the microphone, please? Okay, thanks. That's better. Okay, you can go ahead, Andy.
Okay, thanks. So we thought we'd end the webinar with a brief summary of the planned AI machine learning competition that the S2S project is planning. As some background, the impetus of this is in many ways coming from the WMO, from the Science and Innovation Department and Services and Infrastructure Department, and also the research board of the WMO has identified AI as a key research topic in weather and climate science. And so the hope is that this competition will foster this approach, and specifically encouraging the use of the S2S database. And will support the goals and action areas of S2S, WWRP implementation plan, as well as WCRP. So as been already mentioned, there's a lot of interest in machine learning, and we see the S2S database as some low-hanging fruit here. That's something that could be exploited. And the hope is then the winning entry will push the frontiers of the weather and climate science forward. And a key thing about this competition, maybe in contrast to others, is that this will be entirely open source. So the data, software, code, and results will be made public after the end of the competition. So again, the main goal is competition of any AI ML tool you want to extract valuable information from the S2S database. We have now over 140 terabytes of data in there. And so in terms of the types of machine learning that Peter had outlined at the beginning, we're basically thinking of two types here, either to compete with S2S, which could, so in terms of purely empirical forecasts, so we know there's several of those out there where people are actually using machine learning to make empirical S2S forecasts. So this would be one option to highlight weaknesses or gain fundamental atmospheric research insights, maybe identifying teleconnections and so forth. And the second would be in the post-processing. So to take the forecasts in the S2S database and use them to create more skillful and usable probabilistic forecasts, as we've seen in a couple of the talks today. So for this competition, any data-driven approach could be used. So that could include conventional statistical approaches like model output statistics as well. And what are we going to compare this against? The benchmark will be the ECMWF model with some simple bias correction. Some of the specifics are our targets are going to be 2-meter temperature and precipitation, probabilistic in terms of tercile category probabilities, and the lead times are going to be weeks 3 and 4 and weeks 5 and 6 in terms of biweekly averages of the temperature and precipitation. In terms of the domain, that will be global, but limited to land points and at the spatial resolution of the S2S database, so that's 1.5 degrees. And then in terms of what we'll be verifying and competing on, the target will be the 2020 calendar year, using forecasts issued every Thursday during 2020. So some of the specifics on that, the machine learning algorithm may be trained on any observed data or any reforecast data from the S2S database prior to January 1st, 2020, or any other model database for that matter, SubX, CMIP, large ensemble databases, and so on and so forth. And then no data observed or derived from S2S models from 2020 may be included in the training. However, in the case of the post-processing approaches, the S2S forecast data from 2020 should be used to make the forecasts. In terms of the verification, that will be in terms of rank probability skill score on 3 domains, northern extratropics, tropics, and southern extratropics. And the verification data will come from CPC 2-meter temperature and precip gridded data. So in terms of the implementation, that's going to be hosted by the Swiss Data Center at ETH Zurich using their Renku Lab facility. And that will be making use of Jupyter Notebooks, a binder hub for small prototypes can be actually run at Renku Lab, but it's built on a Git framework. So once it's highly portable, and so heavy lifting can be done elsewhere. Online data access to the S2S database and observed temperature data sets via IRI data library is available, but ECMWF will also be supporting this competition in the newly created European Weather Cloud. So that will provide fast local access to data and possibly CPU time. So for some of the heavy lifting experiments, but they can be done offline on people's own resources. There'll be a leaderboard at SDSC, and we're currently looking for a contractor WMO is looking for a contractor to help run this competition, and the intent is to launch it sometime around April, May, June this year, and then it'll run for 6 months. So the ad for the contractor is still open until the 31st of January. So if you're interested in that, please send an email to Wen Chao at that message, at that address there. And there'll be some small monetary prizes from WMO for the winners. Again, everything will be open source. And I think that's it. Thank you.
Okay, thank
I
you
don't know
very
if you
much.
want to add anything, Frederick, to that, or just take questions.
No, I think that covers
questions there maybe.
Yeah, if people have a few questions, once again in the chat or raising the hand. There's a question from Tim Del Sol. Is there a requirement to use S2S data set in the competition?
It's not a requirement, no. I mean, it's encouraged, but it's not a requirement. For the European weather cloud, maybe if you, Frederick, if you want to say a word about that.
Yeah, just a few words. Well, the European Weather Cloud is a recent initiative, which is a collaboration between ECMWF and EUMETSAT, so to set up a cloud, so to share those data together. So it's getting ready quite now, and yeah, it's under development.
So in terms of Amazon and Google for free computing, we haven't actually got anything lined up from them at the current time. It's a possibility, though, I suppose. We were in contact with Kaggle as a potential host, but in the end, that didn't seem to be suitable. So we've gone with the Swiss data center.
Okay, so I think if there's more question, maybe we can answer in the chat. So I think I will close the webinar now. So thank you all for your attention and for attending this webinar. I would like to thank also APCC for hosting this webinar. I think it worked very well. We will have a next webinar in February, so it will be a bit earlier. Usually that's the last week of the month. Next in February it will be a week earlier, and it will be on the thematic will be on ensembles. So hope to see a lot of you the next month. Okay, goodbye.